learned how to estimate the parameters of the model. So typically we are considering a two-variable regression model. So while we discussed the estimation technique, we learned how to estimate the intercept of the model and the gradient. Anyone, any question regarding the estimation procedure? How we derive the first and second normal equations, and then how simultaneously solving the first and second normal equations, we got to the values of alpha hat and beta hat. Any question regarding that? What is the alpha hat value? Anyone?
Ma'am, y bar minus beta hat x bar.
Very good. Y bar minus beta hat x bar. This is alpha hat. And what about beta hat? What is the value for beta hat?
Covariance xi yi by variance of xi.
Yeah. Or summation xi minus x bar into yi minus y bar.
Y minus y bar by summation of xi minus x bar whole square.
Whole square. Okay. And I think you can remember both the first and second normal equations. First normal equation, what is the first normal equation?
Summation ei is 0.
Summation ei is equal to 0. And what is ei?
That is residual.
Residual. Okay. So the first normal equation is sum of all residuals is equal to 0. While what is the second normal equation?
Summation xi ei is equal to 0.
Summation ei xi is equal to 0. Okay. So this is the context to begin with. So this is the basic estimation. Now, once we estimate the parameters of the model, later we will talk about different context, it may happen that the line is passing through the origin. In that case, there will be no alpha in the model. Okay, y and x will be proportionally related to each other. The structure of the model may be yi is equal to beta xi plus ui. Okay, so under certain circumstances, as you know, the line may pass through the origin. In context of economics, sometimes you consider the consumption function, savings function, which does not have the intercept term, rather it is or supply equation in micro context, which may pass through the origin. Okay, so there may be the context when alpha is not there. In fact, the line is passing through the origin. Okay, so in that case, the value of the beta hat may change slightly. So all these issues are there. However, to begin with, we are considering the standard context, then we will consider all these exercises while we'll start solving the numerical exercises and several other things which are not there in the basic theory. Now, once we estimate the two parameters, alpha hat and beta hat, following the norms of the statistic, we need to assess how good the estimated values are, or how close the estimated values are to the actual values of unknown parameters alpha and beta. To begin with, we are considering the small sample context, and therefore we are trying to check whether these two estimates, alpha hat OLS and beta hat OLS, are MVUE or not, minimum variance unbiased estimators or not. So last day, I started to discuss some properties of the gradient coefficient beta hat. We checked, or we found that beta hat is linear in yi. Okay, beta hat can be presented as wi yi, where wi is xi minus x bar divided by summation xi minus x bar whole square. Okay, so beta hat is linear in yi. Second property, we checked beta hat is an unbiased estimator of beta. Beta hat OLS is an unbiased estimator of beta. So that property also we checked. So today we have to focus on the minimum variance property, whether among all possible estimators or unbiased estimators of beta, whether beta hat OLS is giving us minimum variance or not. As I mentioned last day, it will consist of two parts. In the first part, we have to calculate the variance of beta hat OLS, because so far we didn't have knowledge about what is the variance of beta hat OLS. We know expectation of beta hat OLS is equal to beta. However, we have no knowledge about variance of beta hat OLS. So in the first step, I have to calculate what is variance of beta hat OLS. After that, we will consider some other unbiased estimator of beta, not OLS, some other unbiased estimator of beta, and we need to compare the variance of beta hat OLS with that any other unbiased estimator of beta. As you learned in your earlier semester, both with unbiasedness as well as in context of large sample consistency, these two properties are not unique. These are very important properties. However, the limitation of the properties are, these are not unique. We can generate a number of unbiased estimator, or we can generate a number of consistent estimators. Okay. And for that matter, if it is a large sample, we have to consider the speed of convergence of the variance, which we call the efficiency property. Whereas in the small sample, we have to consider the minimum variance property. Okay. So keeping all these things in our mind, we will proceed. So today, first we will start with calculation of variance of beta hat OLS. And after that, we will consider any other unbiased estimator of beta and compare the variances of the two. Any question, any query so far? I hope you have pen and paper with you. So sometimes it is always best to at least put some matters in the copies, if not the entire derivation, So if you feel you can do the entire derivation while we are discussing the matter, or if you feel that you will put several things as note, you can keep the things like that. Okay, now, at the top, there is some information regarding alpha hat. Regarding alpha hat, all the information I'll give together, So after completing the properties of the beta hat, when I'll start talking about the properties of alpha hat, I'll give all information regarding the unbiasedness minimum variance property. Together I'll discuss the matters. So please concentrate on best property of beta hat, best property of beta hat OLS. Typically, we are talking about beta hat OLS because we estimated the parameters using the OLS technique. So look at the projection. Variance of beta hat, the standard formula is expectation of beta hat minus expectation of beta hat whole square. Expectation of beta hat minus expectation of beta hat whole square. Now, already we proved that expectation of beta hat is equal to beta. That is, beta hat OLS is an unbiased estimator of beta. So I am replacing this expectation of beta hat by beta. Okay. So the variance is expectation of beta hat minus beta whole square. Now let's go back. Since I'm doing the exercises, one by one, therefore I'm not doing all the steps because I have the steps. However, when you will do this thing for exam purpose, or for your practice purpose, you will do the steps by which you will be able to reach at this position. That is, beta hat minus beta can be replaced by summation Wi ui. Okay. So let's see how I'm doing that. Okay. So look at this step. Look at this step. Last day, we found that beta hat is equal to beta plus summation Wi ui. Okay. We started with this beta hat, and then we considered the value Wi, which is xi minus x bar divided by summation xi minus x bar whole square. And putting the matters, we got beta hat is equal to beta plus summation Wi ui. So naturally, beta hat minus beta, that is nothing but summation Wi ui. So I'm using this step. I'm using this step. However, you need to do all these steps to reach at this position. Now in the question, if simultaneously you need to check expectation of beta hat is equal to beta and variance of beta hat you need to find out. In that case, you don't need, because already the steps will be there when you will calculate expectation of beta hat. However, if the expectation part is not there in the question, then you need to reach at this step. Okay, whatever be the thing, look at this step, and I hope all of you are getting beta hat minus beta is nothing but summation wi ui. So in place of beta hat minus beta, I'm putting summation wi ui. I'm putting summation wi ui in place of beta. Okay, everybody, is this part clear? How from expectation of beta hat minus beta whole square I'm coming to this? Is it clear to all of you?
Yes, ma'am.
Yes, sir.
Okay, Shreya, roll number 4, Shreya. Is it okay?
Yes, ma'am.
Okay. Anyone else who has any problem regarding this thing? If you have any problem, please let me know. If required, I'll show you how I'm getting summation wi ui. Okay. Okay. So if you get, it is expectation of summation wi ui whole square. So basically it is expectation of w1 square it is summation of wi ui whole square. Okay, so that means w1 u1 plus w2 u2 up to plus wn un whole square of that. So you will get the square values and you will get the cross products. And so on. Sorry. W, you can, okay. W n minus 1. So all these things you will get. It's a big thing, it's a big thing. So better to write the expression as so better to write this expression. Expectation of summation wi ui whole square plus double summation I is equal to 1 to n, j is equal to 1 to n, I not equal to j, wi wj ui uj. Everybody? Expectation of summation wi ui whole square, can we present this in this format? Expectation of summation wi ui square plus double summation I is equal to 1 to n, j is equal to 1 to n, I not equal to j, wi wj ui uj. Is it okay? Is it acceptable?
Yes, ma'am.
Yes, ma'am.
Okay, so we are at this step. Now I have to operate expectation. Okay, I have to operate expectation on all the terms. So in the first part, when I'm writing summation wi ui whole square, summation wi ui whole square, basically I have is it okay? If I operate expectation on this term, wi is xi minus x bar divided by summation xi minus x bar whole square, and for using the convention, I'm considering xi to be non-stochastic. So can we write the first term while operating the expectation in this way?
Yes, ma'am.
Ma'am,
Just a minute. Yes, somebody had some question?
ma'am, shouldn't that first term wi be wi squared times expectation of ui squared?
Yeah, definitely. Definitely. So this is the thing.
Ma'am,
Yes.
ম্যাম বলছি ওই এক্সপেকটেশন অফ সামেশন ডব্লিউ আই ইউআই হোল স্কোয়ারের যে মানে সেটা এক্সপ্যান্ড করলে কিরকম হবে একদম লাস্ট লাইনে যেটা লিখলেন একটু বলবেন, মানে যেটা কি কোভেরিয়েন্স টার্ম নিয়ে যেটা আছে আর ডাবল সামেশন।
এটা
ইয়েস ম্যাম, হ্যাঁ ওটা একবার রিড করবেন।
আচ্ছা, এটা লিখেছি double summation I is equal to 1 to n, j is equal to 1 to n, I not equal to j, wi wj ui uj. Actually this is wi ui into wj uj, what which I can write as wi wj ui uj. I kept
ওকে ম্যাম, থ্যাংক ইউ।
uj together because in the next step I'll take the expectation. Expectation will be operated in this on this product ui uj, and for that matter I kept ui uj together. Is it okay?
ইয়েস ম্যাম।
Okay, so everybody I think is at this step. Summation I is equal to 1 to n wi square expectation of ui squares double summation wi wj expectation ui uj. Now can you tell me what is the value of expectation of ui square? Is there any assumption regarding this one? Is
Ma'am,
there
sigma
any?
squared u. Ma'am, homoscedasticity.
Very good. So there is homoscedasticity assumption. Expectation of ui square is nothing but variance of ui. Okay, so if we go back a little bit. Okay, so expectation of ui square is nothing but variance of ui. Actually, variance of ui is equal to expectation of ui minus expectation of ui whole square. Expectation of ui is equal to 0. So variance of ui is simply expectation of ui square, which is sigma u square, a constant. So by homoscedasticity assumption, expectation of ui square is nothing but a constant given by sigma u square. And another thing, another assumption we discussed, covariance between ui uj, which to begin with expectation of ui minus expectation of ui uj minus expectation of uj, which reduces to simply expectation of ui uj, as expectation of ui and expectation of uj are equal to 0. That is equal to 0, which we are calling the non-autocorrelation assumption. So we will operate both the assumptions in this context. Okay, and this we will write as you how to do undo here. Okay, so sigma u square summation wi square. Sigma u square, all of you told that this is homoscedasticity assumption, so it is a constant. We can keep it outside the range of the summation. Okay, and this expectation of ui uj, this by assumption of non-autocorrelation is equal to 0. So the entire second term vanishes. Okay, the second term will be not there. The second term will be not there. Okay, so simply I'm getting this to be equal to sigma u square into summation wi square. Please add since expectation of ui square is equal to sigma u square, since expectation of ui square is equal to sigma u square and expectation of ui uj is equal to 0. Expectation of ui square is equal to sigma y u square by the assumption of homoscedasticity. So please add by the assumption of homoscedasticity. And expectation of ui uj, this is equal to 0 by the assumption of non-autocorrelation. By the assumption of non-autocorrelation. Okay, so everybody is there with the term sigma u square summation wi square. Everybody could understand up to this? Up to this step? Okay.
Yes, ma'am.
Next, please concentrate on this note. On this note. So we will present summation wi square in terms of the variables of the model. Summation wi square is equal to summation xi minus x bar divided by summation xi minus x bar whole square of the entire thing. Because wi is xi minus x bar divided by summation xi minus x bar whole square. So I hope you are understanding you have to take whole square of the entire matter. Okay, so if you do so, if you consider it is summation of whole square of the entire matter, your numerator is summation xi minus x bar whole square and the denominator is already summation xi minus x bar whole square. So you have to take square of this. You have to take square of this. So in the numerator, you have one summation xi minus x bar whole square. In the denominator, you have two summation xi minus x bar whole square. Actually, summation xi minus x bar whole square into summation xi minus x bar whole square. So one summation xi minus x bar whole square will be cancelled and you will finally get the ratio 1 by summation xi minus x bar whole square. 1 by summation xi minus x bar whole square. Okay. So if I move to this state, sigma u square summation wi square, so finally the variance value is nothing but sigma u square divided by summation xi minus x bar whole square, sigma u square divided by summation xi minus x bar whole square. So everybody should write variance of beta hat is therefore this is the formula for variance of beta hat, sigma u square divided by summation xi minus x bar whole square. This can be presented using the notation sigma u square divided by variance of capital Xi, or as I mentioned, capital Xi minus x bar is equal to small xi. Small xi is nothing but capital Xi minus x bar. So if you use that notation, it is simply sigma u square divided by summation small xi square. So the basic formula is variance of beta hat is equal to sigma u square divided by summation xi minus x bar whole square You can present it as sigma u squared divided by variance of cap xi, or you can present it as sigma u squared divided by summation of small xi squared, where small xi is equal to capital Xi minus x bar. Any question? Any question or anything I need to repeat?
ম্যাম লাস্ট স্টেপটা আরেকবার একটু বলুন।
তুমি এটা বুঝতে পেরে গেছিলে সামেশন?
হ্যাঁ হ্যাঁ হ্যাঁ, ওটা সিগমা ইউ স্কয়ার বাই ভেরিয়েন্স এক্সআই বুঝে গেছি।
হ্যাঁ, sigma u square by variance xi মানে তোমার sigma u square divided by summation capital Xi minus x bar whole square. This is becoming the formula.
হ্যাঁ
ওকে,
আচ্ছা
এবার summation xi minus x bar whole square ওটাকে এইভাবেও প্রেজেন্ট করে অনেক বইতে, sigma u square divided by variance of xi. ওকে, মানে ওই 1 by n টাকে ইগনোর করো, sigma u square divided by variance of xi। আর এই নোটেশনটা খুব পপুলার, capital Xi minus x bar is equal to small xi. This notation is also very popular. Capital Xi minus y bar is equal to small yi. So if you follow, we call these things the deviation form. Actually, capital Xi minus x bar means deviation of all observations from the mean value. Capital Yi minus y bar again indicates the same thing, deviation of all yi values from its mean value. Okay, so a number of text or reference books use the notation small xi in place of capital Xi minus x bar and small yi in place of capital Yi minus y bar. Okay, so if you use that kind of notation, that is, you use the deviation form, in that case you can simply write sigma u square divided by summation Xi minus x bar whole square as sigma u square divided by summation small xi square. Is it now okay, Rajdeep?
Yes, ma'am.
Anyone, any other question? Lakshadip?
Yes, ma'am.
বুঝতে পারছো সব?
হ্যাঁ ম্যাম, বুঝতে পারছি।
সব বোঝা গেছে? বর্ষা? হ্যাঁ, কারোর একটা কোয়েশ্চেন আছে, বলো।
আমি বলছিলাম যে একদম প্রথমেতে এক্সপেকটেশন অফ বিটা হাইট মাইনাস বিটা স্কোয়ার, ওইটার জায়গায় সামেশন ডব্লিউ আই ইউআই টা লিখেছেন।
বিটা হ্যাট মাইনাস বিটার জায়গায় সামেশন ডব্লিউআই ইউআই টা লিখেছি। কি করে লিখেছি? বিকজ লাস্ট ডে আমি ডেরিভেশনটা করেছি। From the derivation of the last day, we find that beta hat is equal to beta plus summation wi ui. So beta hat minus beta is equal to simply summation wi ui. So that I have used here.
ওকে ম্যাম।
So we have the variance formula in our hand. This is sigma u square divided by summation xi minus x bar whole square. With this knowledge, I'll consider any other unbiased estimator of beta and compare and calculate the variance of that estimator, that alternative estimator, and then I'll compare the variances of the two. Remember that when you are going to compare the variances of the two estimators, otherwise the estimator will be very much similar to that of OLS. That is, that should be linear in yi and that should be unbiased. Okay, so these two properties which I discussed before considering the variances, these two properties will be similar, identical for the two estimators. These two properties will be identical for the two estimators. Okay, because otherwise the estimators will be not comparable. So keeping these points in our mind, That is, we have to talk about or calculate the variance of any other linear unbiased estimator, and then we need to compare the two. We are proceeding for the next step. It can also be shown that among the class of all linear unbiased estimators of beta, this OLS estimator beta hat is the best in the sense of having minimum variance. So we can show that beta hat OLS is MVUE, minimum variance unbiased estimator. Now, if beta hat follows both the unbiasedness and the minimum variance property along with linearity, we call beta hat OLS the best linear unbiased estimator. Best for minimum variance, linear you are understanding, unbiased you are understanding, estimator you are understanding. Okay, so this U will be not there. You know, best linear unbiased estimators, blue. So beta hat OLS is called the blue best linear unbiased estimator. Okay. Under the classical framework, that is under the classical assumptions, all classical assumptions we have considered regarding the random error term UI, that is the unbiasedness of random error, homoscedasticity, non-autocorrelation, covariance between xi ui is equal to 0, and ui follows normal distribution. So under these 5 classic assumptions regarding the random error term, if we find that the estimated value is a best linear unbiased estimator, that follows the famous Gauss-Markov theorem. Gauss-Markov theorem. So please note down this line. I'm coming. Just 1 minute. Okay, so have you taken the note about this? Is
Yes,
it clear?
ma'am.
Okay. So under the classical assumptions or under the classical setup, if we can generate OLS estimator, which is blue, that covers the famous Gauss-Markov theorem. Okay, so now I'm going to prove that beta hat OLS is the best estimator. So let's propose another linear unbiased estimator of beta, say beta tilde. Okay, another linear unbiased estimator. As I mentioned, rest of the properties will be identical. Rest of the properties will be identical. Otherwise, the estimators will be not comparable at all. So, linear and another linear unbiased estimator of beta, that is beta tilde we are considering, and we have to compare variance of beta hat OLS and variance of beta tilde. We are proposing a linear estimator. So, to begin with, I am writing beta tilde is equal to summation Ci yi. Please read all these yi's as capital yi and all xi is capital xi, okay? Because we are following a particular type of notation, you know, and I didn't get time to redo the entire thing. So please consider while you are writing, write all these yi as capital yi and all these xi's are capital xi's, okay? So please do so. So all these are capital. So beta tilde, I'm considering summation CIYI. Now, how we presented beta hat OLS? Beta hat OLS we presented as summation WI YI. In this way we presented beta hat OLS. Okay, so we are following the similar kind of format. Beta tilde is equal to summation CIYI, where CI is non-stochastic and CI is equal to WI plus DI, where DI is not equal to 0 and also non-stochastic. CI itself is non-stochastic. Just a minute. So all the components of CI, that should be non-stochastic. Okay. Already we have defined WI. Here with WI, this DI may be positive, DI may be negative. Okay. However, non-zero. So I am adding one non-zero element. It is not equal to 0. It can be positive, it can be negative. Any other element, Just I'm changing WI a bit. That was WIYI. Here it is CIYI. In CI, one component is WI, another component is DI. DI can be positive, DI can be negative. However, non-zero. Yes. Somebody had question?
না ম্যাম ঠিক আছে বুঝে গেছি
Okay.
ম্যাম বলছি এখানে কি প্লাসই করতে হয়, মানে ইনটু করা যায় না, মানে প্লাস ছাড়া অন্য কিছু?
কোনটা? CI-টা?
মানে ওই যে সিআই কল না, সিআই কল টু WI প্লাস DI, ওই প্লাসটাই কি সবসময় করতে হবে না, ইনটু বা ডিভাইডেড অন্য কিছু করা যায়?
প্লাসটাই করতে হবে। প্লাসটা করা মানে প্লাসও করছো মাইনাসও করছো, কিন্তু হ্যাঁ,
আচ্ছা আচ্ছা,
ইজ নট ইকুয়াল টু 0। হ্যাঁ, তুমি তো লিনিয়ারিটি মেনটেন করছো, এবারে তুমি এবার প্রোডাক্ট নিয়ে আসবে, প্রোডাক্ট নিয়ে তাহলে আবার একটা অ্যাজাম্পশন লিখতে হবে। ওকে, সো
আচ্ছা
okay, I want a linear unbiased estimator, an alternative linear unbiased estimator. So it is preferred that you will consider summation. Okay, however, remember that DI can be positive, negative. It is a non-zero, non-stochastic part. That's all. Okay, so beta tilde, this is equal to summation CI. I'm replacing YI by the basic regression, alpha plus beta xi plus UI, because I need to check whether expectation of beta tilde is unbiased, or I need to consider different constraints following the unbiasedness condition. So I have to develop the matter. So I need to bring UI, the random error term, in the context, because all the classical assumptions, as you know, center around the random error term UI. Okay, so beta tilde is this. So this can be presented as alpha summation CI plus beta summation CI xi plus summation CI UI. Just I'm splitting the sum for the 3 elements. Okay, simple thing. In the next step, I have in my hand another property apart from linearity, unbiasedness. I'm posing beta tilde in such a way it is a linear and unbiased estimator of beta. So the precondition of considering beta tilde is expectation of beta tilde is equal to beta. The precondition of considering beta tilde to compare the variances is beta tilde should be an unbiased estimator of beta. Everybody agreeing with this matter? This is a precondition. Otherwise, the things will be not complete.
yes, ma'am.
Okay, got it? Everybody?
Yes, ma'am.
Okay, Shoham is there. Roll number 3 is there today. Protush, are you there?
Yes, ma'am.
Understanding the matters?
Yes, ma'am. বুঝতে পারছি।
Okay. So expectation of beta tilde is equal to beta. This is a precondition to consider beta tilde to check the variances, etc. Now, expectation of beta tilde is equal to beta if in this equation summation ci is equal to 0 and summation ci xi is equal to 1. Expectation of beta tilde will be equal to beta if summation ci is equal to 0. So if summation ci is equal to 0, the first thing will vanish. If summation ci xi is equal to 1, it will be beta. So in that case, if you take expectation of beta tilde, expectation of beta is beta since beta is a constant, plus summation ci, expectation of ui is equal to 0 by the first assumption. So finally, we will get expectation of beta tilde is equal to beta. So is this line acceptable to all of you? Any query, any question? For is if and only if part? Any question? So I'm getting two constraints. Okay. So I'll minimize subject to these constraints while we will proceed further. So I hope everybody is understanding. While we are putting all these things, bringing CI, okay, the preconditions are generating two constraints in the framework. One is summation CI should be equal to 0 and another is summation CI xi should be equal to 1. Now summation ci is equal to 0, that is equivalent to summation wi plus di is equal to 0 because we have defined ci in this way. This implies summation wi plus summation di is equal to 0. Now what is wi? Xi minus x bar divided by summation xi minus x bar whole square. So when we consider summation wi, we get summation xi minus x bar in the numerator, which is nx bar minus nx bar, and for that matter, summation wi is equal to 0. Already we checked all these things earlier. So is there any doubt regarding this part, that is summation wi is equal to 0? Do I need to clarify it once again? Is this clear?
Yes, ma'am.
Okay. So if summation wi is equal to 0 and the equation is summation wi plus summation di 0, naturally it implies summation di is equal to 0. So I'm not considering the constraints in terms of CIs, rather I am simplifying the matter and putting the constraints in terms of DI. So the first constraint we are getting, that is summation BI is equal to 0, which we are calling equation number 1. So this is the first constraint. The second requirement was summation CI xi is equal to 1. By the way, please read this xi as capital Xi. Okay, and this xi2, this xi2, this xi2. So summation CI xi is equal to 1. This implies summation wi plus di into xi is equal to 1. This implies summation wi xi plus summation di xi is equal to 1. Can you remember what is the value of summation wi xi?
1.
1. Already we
Yes,
proved
ma'am.
summation wi xi is equal to 1. Now if summation wi xi is equal to 1 in this equation, if this part is equal to 1, in that case, if their sum is equal to 1, naturally this part should be equal to 0. Everyone?
Yes, ma'am. Yes, ma'am.
So since summation wi xi is equal to 1, therefore summation di xi is equal to 0. Okay, capital Xi. So the second constraint in our framework is given by summation di xi is equal to 0, which we are calling equation number 2. Got it? So two constraints are clear to all of you. The first constraint, equation number 1, summation di is equal to 0. The second constraint, summation di xi is equal to 0. Next, we are considering beta tilde. Beta tilde is equal to beta plus summation ci ui. So let me check. Summation ci is equal to 0. Summation ci xi is equal to 1. So beta tilde is equal to beta plus summation ci ui. Beta tilde is equal to beta plus summation ci ui. Okay, so this is beta tilde. Now variance of beta tilde, that is expectation of beta tilde minus expectation of beta tilde whole square, like any other estimator. Expectation of beta tilde is equal to beta because we are considering beta tilde in such a way so that it is an unbiased estimator of beta. So it is expectation of beta tilde minus beta whole square. Now beta tilde minus beta, that is summation ci ui. So it is expectation summation ci ui whole square. Okay. So this is equal to okay. And then you do the next step and then check whether you can reach at this step or not.
Yes, ma'am.
Okay, so I hope you could complete the steps and could reach up to this. Anyone has any problem from this step? Could you reach to this? You have to take expectation of ui square. Sorry. The square will be there. Okay. Expectation of ui square is sigma u square. And this expectation of ui uj is equal to 0. So simply it will be this one as first one is the homoscedasticity assumption and the second one is the non-autocorrelation assumption. So everybody, I hope, got variance of beta tilde is equal to sigma u square into summation ci square. Any question?
No, ma'am.
Okay. So this summation ci square part is there. So we need to check whether this summation ci square is equivalent to summation wi square. Let us check what we got in case of this one. Okay. So we got this value, sigma u square into summation wi square. And here we are getting sigma u square into summation ci square. So main comparison is in between this summation wi square and summation ci square. Okay. So comparison will be in between summation ci square and summation wi square. Otherwise, these are very, very similar. This one is sigma u square into summation wi square, and for the alternative estimator, it is sigma u square into summation ci square. So we need to compare, or we need to clarify what actually summation ci square indicates. Now summation ci square, that means summation wi plus di whole square, which is summation wi square plus summation di square plus 2 summation di wi. Summation di square is strictly positive. Okay. And summation wi square was there in case of OLS. So we will concentrate on this part. So if last 2 summation di wi is exactly equal to summation di square, sorry, if you know, and the value is negative, actually, if 2 into summation di wi, negative of that value is equal to this one. In that case, these two things will cancel each other. If this is equal to this minus of this, in that case, these will cancel each other. And we will find that for the alternative estimator too, the variance value is same. The variance value is similar to that of the OLS one. Now, if I can show that this part is positive, summation di square is strictly positive. So if this part is also positive, in that case, definitely it will be greater than summation wi square. If we can show this part is equal to 0, in that case also, since plus di square, summation di square is strictly positive, in that case also summation ci square will be greater than that of summation wi square. So we need to concentrate on this part. What is the value of summation di wi? What is the value of summation di wi? Because summation di square is strictly positive. So if we look at the value of summation di wi, it is di capital Xi minus X bar all caps divided by summation Xi minus X bar whole square. So I am keeping 1 by summation Xi minus X bar whole square outside. So it is summation di into Xi minus X bar. Okay. So it is summation di Xi minus X bar into summation di. Okay. And already we have two constants, equations 1 and 2. One is summation di is equal to 0. So if you put this restriction here, the second term will vanish. And we have another restriction, which is equation number 2, that is summation di xi is equal to 0. So if I put that restriction, this first part will be also vanish. So this entire thing is equal to 0. So summation di wi is equal to 0. So what we are finding that summation ci square is equal to summation wi square plus di, summation di square, where summation di square is strictly positive. Okay, so variance of beta tilde is sigma u square summation ci square, which is equal to sigma u square summation wi square plus sigma u square summation di square. Sigma u square summation wi square is the variance of beta hat ONS, and this part is extra. So variance of beta tilde minus variance of beta hat is a positive quantity. So safely we can argue variance of beta tilde is greater than that of variance of beta hat ONS. So we considered a very, very close estimator to OLS, very, very similar otherwise. However, we are finding that variance of beta tilde is greater than that of variance of beta hat. So we can argue that beta hat OLS is the minimum variance unbiased estimator for beta. Any question? Is it okay?
Ma'am,
Yes.
বলছি সামেশন অফ ডিআই স্কোয়ার ওটা স্ট্রিক্টলি পজিটিভ কেন একটু
If you consider the square of any term, positive or negative, there is a chance that
ডিআই স্কোয়ার, হ্যাঁ হ্যাঁ ঠিক আছে
di
ম্যাম
itself
বলছি
is negative. It is non-zero element. However, when you are getting di square, no way, it should be strictly positive.
ইয়েস ম্যাম।
ম্যাম বলছে একবার আগের স্লাইডটাই যাবে।
What is the question?
ম্যাম আমি একটু লিখে নিচ্ছি, একটা পার্ট একটা লেখা বাকি আছে।
For rest of the students, any question, any query?
হয়ে গেছে ম্যাম।
Okay. Very good.
Ma'am,
Yes.
ma'am, beta tilde is representative of all linear unbiased estimators apart from beta hat, right?
Yes. Yes. Because Ti is any arbitrary element, you know. So therefore, it is any other estimator, any other linear unbiased estimator, any other. Okay. So this is all about the properties of beta hat OLS. OLS generally we apply in context of small sample. So we do not consider the consistency as well as the efficiency properties here. So we are thinking about a finite sample, and for that matter, we are considering the minimum variance and the unbiasedness properties. Okay. So this is all about beta hat. Next, we have to discuss the matter for alpha hat, whether alpha hat is unbiased estimator. Linearity we will not consider because it is the intercept term. So we have to consider whether alpha hat is unbiased estimator. And number two, what is the variance of alpha hat? And from the set of unbiased estimators of the intercept, whether variance of alpha hat is giving the minimum variance or not. Okay, so properties of alpha hat. alpha hat is equal to y bar minus beta hat x bar. So just like the previous one, so you consider the notations to be capital. Okay, so all these values are capital basically. So what we are doing, y bar minus beta hat x bar. Then I am writing the value of y bar. I'm replacing y bar by alpha plus beta x bar plus u bar. Now, how we got this thing? So summation yi is equal to, what will be the first term?
n alpha.
N alpha. Then
beta summation xi.
Beta summation xi plus nui.
plus
Oh,
Nui.
nu.
No, summation ui. Sorry. No, summation ui.
And then we are dividing both sides by n. Okay. So y bar is equal to alpha plus beta x bar plus u bar. So here I'm using, in place of y bar, alpha plus beta x bar plus u bar. Minus beta hat x bar is already there. In the next step, I'm taking x bar common. So alpha minus beta hat minus beta x bar plus u bar. So is this step okay? Alpha hat can be written in this way. Is it okay?
Yes, ma'am.
If this is clear, next step, expectation of alpha hat. Expectation of alpha hat is equal to expectation of alpha, which is equal to alpha minus expectation of beta hat. Expectation of beta is simply beta into x bar, expectation of u bar. Now expectation of beta hat is beta, so this term will be equal to 0. You are getting the value alpha here. And what about expectation of u bar? Expectation some expectation of ui is equal to 0 by the first assumption of unbiasedness. Hence, expectation of u bar is also equal to 0. So thus finally we can write expectation of alpha hat is equal to alpha. Is it clear? Any question? All these steps, which I'm putting in the side, you need to do all these things. Otherwise, the things will be not clear.
ওখানে ডাইরেক্ট এক্সপেকটেশন অফ ইউ বার ইকুয়াল টু 0 লিখলে হবে না, মানে অ্যাজাম্পশনে?
I didn't get you.
ম্যাম আমি বলছি এক্সপেকটেশন অফ ইউ বার ইকুয়াল টু 0, ওটা যদি লিখে দিই, মানে আমাকে কি ডিরাইভ করে দেখাতে হবে কেন 0 হচ্ছে?
দেখো বিভিন্ন সময় তো all these contexts come, and we find that students are not understanding, the how expectation of u bar is equal to 0. So it's better to practice all these things and put the matter like this.
Okay, ma'am.
Okay, so this is all about the first property. Expectation of alpha hat is equal to alpha. Second, first we need to calculate the variance of alpha hat. After that, we will consider another unbiased estimator of alpha and we will compare the variances of the two. So let's first put the variance of alpha hat, put the value of variance of alpha hat, or how we estimate alpha hat. Okay, so you do all these steps and after that we will have a break and then I'll go for showing this is the minimum variance. Okay, so
আগের স্লাইডে একবার যাবেন
yeah, any question?
ম্যাম আগের স্লাইডটা একবার যাবেন আগের slide? হ্যাঁ ম্যাম ঠিক আছে
So variance of alpha hat. Variance of alpha hat, the standard formula will be expectation of alpha hat minus expectation of alpha hat whole square. Now, expectation of alpha hat is equal to alpha because already we proved alpha hat OLS is an unbiased estimator of alpha. So it is alpha. Now I am replacing alpha hat minus alpha in terms of the variables of the model. So let me check. Alpha hat was alpha minus beta into x bar plus u bar. So alpha hat minus alpha, that will be minus beta into x bar plus u bar. So u bar minus beta x bar. I'm replacing alpha hat minus alpha by this term. Is it okay? After that, I'll consider the whole square. So it is, what you can do, first you take the whole square, then in the next step you operate expectation. Here, simultaneously I have done the thing. I am taking the whole square and operating the expectation. It will be better if you do it in two steps. So you keep expectation as it is. This whole square is becoming u bar square plus beta hat minus beta whole square into x bar square minus 2 x bar into beta hat minus beta into u bar. So first you write down that step. After that, you operate expectation on each of the three terms. So you will get expectation of u bar square, x bar square into expectation of beta hat minus beta whole square minus 2x bar into expectation of beta hat minus beta into u bar. So please let me know whether you understood up to this or could complete up to this. Is it okay? Is there anyone who could not understand? Could you complete up to this?
Yes, ma'am.
Yes, ma'am.
Okay. So next we have to find out the values of expectation of u bar square, etc. All these things are there. Are you understanding the first term? Can we write expectation of u bar square is equal to sigma u square by n? Madhusri, how we are getting this? Oh, sorry, Rupasri. Sorry. How we are getting this? Are you there? Can I discard the things? Actually, if I want to come out, I have to discard the things. Anyone, please tell me how we can write expectation of u bar square.
ম্যাম
Yes, Rajdeep.
ম্যাম হ্যাঁ বলছি ইউ বার স্কোয়ারটাকে আমি যদি লিখি সামেশন অফ ইউআই বাই এন হোল স্কোয়ার, আর তারপরে তারপরে যদি আমি এক্সপেকটেশন ভিতরে ইয়ে করি, মানে এক্সপেকটেশন নিলে তাহলে ওটা চলে আসবে মানে এক্সপেকটেশন অফ সামেশন ইউআই স্কোয়ার।
Summation expectation of ui square.
হ্যাঁ মানে সরি, সামেশন এক্সপেকটেশন অফ ইউআই স্কোয়ার, যেটা সিগমা স্কোয়ার হয়ে যাবে, আর নিচে সিগমা স্কোয়ার থাকবে আর নিচে এন থাকবে।
ওপরটা
হ্যাঁ
সিগমা
ম্যাম।
কি? ওপরটা
ম্যাম
সিগমা
উপরটা এন সিগমা স্কোয়ার থাকবে।
হ্যাঁ, n sigma square আর ডিনোমিনেটরটা
এন স্কোয়ার থাকবে।
n square. Very good. So cancellation of 1n, finally sigma u squared by n. That will be the result. Okay. So expectation of u bar square as he said, okay, actually here the covariance part is also coming. Okay. Because it is, you know, u1 plus u2 up to un whole square. Rajdeep, isn't it?
ম্যাম হ্যাঁ, কিন্তু ওটা যেহেতু সিএলআর এম আছে তাই জন্য আমি ওটা বলিনি।
This is the right formula.
হ্যাঁ হ্যাঁ মানে
Ma'am,
Just a minute. Yes. Somebody had some question? Yes.
ma'am, we get that no autocorrelation, right?
There is no autocorrelation. Yes. So I hope everybody understood how we got the first value. Expectation of u bar square is equal to sigma u square by n. The second term was x bar square, expectation of beta hat minus beta whole square. Now expectation of beta hat minus beta whole square is nothing but variance of beta hat OLS. This is nothing but variance of beta hat OLS because it is expectation of beta hat minus expectation of beta hat whole square of that. So it is variance of beta hat OLS. Okay, so x bar square, it will be as it is, and it is sigma u square divided by summation xi minus x bar whole square. Okay. Any question regarding the second term? Simply, I am putting the value of variance of beta hat OLS, which is sigma u square divided by summation xi minus x bar whole square. And now I'll work with the third term. What about the third term? 2 into x bar into this term. So first I am considering the expectation of u bar into beta hat minus beta. Now beta hat minus beta, that is summation wi ui, summation wi ui. And u bar is summation ui by n. So if I consider u bar to be summation ui by n and beta hat minus beta summation wi ui, we can write it is expectation of summation wi ui square by n. Okay, 1 by n I am keeping outside the range of sum, summation wi expectation of ui square. So please tell me whether you are understanding this matter or not.
Ma'am, can you repeat the last part?
This part.
That expectation U bar into summation WI UI part, the last part.
This one.
But the third last line.
U bar is summation ui by n. So I have summation wi ui. Ui already is there. If I write here summation ui by n, that I bring with these ui, actually better to so this is summation ui by n, and I have sorry. Okay. So you have W1, U1 plus W2. So what you can do, 1 by n you keep as it is. W1 can you do this? You will get all this term. Plus you will get the cross products. Got it? So you are getting summation wi ui square, and there are several other elements too. And when you will consider the expectation of that part, actually here, what you can do, you can keep that ui uj component too. Or, you can bring expectation here, so that instead of keeping expectation here, so that I hope you are understanding expectation of ui uj this part is equal to 0. So safely I can consider summation wi into expectation of ui square component. Is it understandable now?
Yes, ma'am. Yes, ma'am.
So it is always better if you can, spread the series and try to understand what is happening. Some student asked whether directly I can write expectation of u bar is equal to 0. Yes, you can. However, you need to understand the matter. Thank you that you raised the question so that I gave you the entire thing. Just a minute. Hello? Okay, okay. Hmm. Okay, so is the thing clear to all of you? দেখো সব স্টেপস গুলো করতে পেরেছো?
Yes, ma'am.
ইয়েস ম্যাম।
আচ্ছা, সো if you do these things, আচ্ছা এইটা তাহলে ultimately is equal to 1 by n summation wi expectation of ui square. Expectation of ui square is sigma u square. So it is sigma u square by n into summation wi. Summation wi is equal to 0. So this entire part is equal to 0. Okay. Thus, the variance of alpha hat, this is sigma square by n plus x bar square into sigma square divided by summation xi minus x bar whole square. That is variance of alpha hat is equal to sigma square by n plus x bar square into variance of beta hat. So please write down variance of alpha hat is equal to sigma square by n plus x bar square into variance of beta hat. Okay, so let's have a break for 10 minutes and then we will complete the minimum variance property. Okay, so I'll start from 12. এখন কটা বাজে? 12:05, 12:15. Okay, so I'll start from 12:15. So we are here. Variance of alpha hat is equal to, you can write the thing in this way too. Sigma u square you can take common and you can write the thing in this way too. So let's stop here, and all these x here, that should be capital. This you can write sxx with the small notation because it is indicating summation small xi square. So this part basically indicates summation small xi square notationally. So this you can keep small x. Okay, so I'm coming after 10 minutes. So let me first check the attendance. Roll number 1. What about roll number 1? Oishi, Shreya?
Ma'am, he is having exams of actuaries. I think today is his last exam.
Okay. Okay. Yatush?
Yes, ma'am.
সোহম?
প্রেজেন্ট ম্যাম।
সোহম ছিলে প্রথম থেকে?
ইয়েস ম্যাম।
বুঝতে পারছো সব?
হ্যাঁ হ্যাঁ হ্যাঁ।
শ্রেয়া?
Present, ma'am.
রাজদীপ?
প্রেজেন্ট ম্যাম।
সুষমা?
Yes, ma'am.
গৌসিয়া?
Yes, ma'am.
শ্রেয়সী? Shreyashi is absent. Shreya?
Present, ma'am.
Abhishek?
Present, ma'am.
Annesha?
Present, ma'am.
Ritanu? Ritanu? বর্ষা?
রিতনু চ্যাট বক্সে লিখেছে প্রেজেন্ট আছে।
বর্ষা?
Present, ma'am.
মেহুলি? শিবানী?
Present, miss.
সুকন্যা?
Present, ma'am.
শ্রেয়সী?
প্রেজেন্ট ম্যাম।
সৃজিতা?
প্রেজেন্ট ম্যাম।
সিঞ্জিনী? প্রিয়াঙ্কা? ঐশ্বর্য?
Yes, ma'am.
সাবনিক? আরাত্রিক?
Yes, ma'am.
Dhruv, Lakshadip,
ম্যাম ম্যাম
Present,
মেহুলি
ma'am.
ও চ্যাট বক্সে লিখেছে।
Dhruv.
না না মেহুলি।
Okay, Mehuli. Mehuli chat box.
ম্যাম 16 বোধ হয়।
16, no? So, Srijoni,
Present, ma'am.
Oishi,
Present, ma'am.
Ratu,
Present, ma'am.
Rupostri, Shayoni, Dibbatanu, Orko, Olipriya,
Present, ma'am.
Dighi, Amit,
Yes, ma'am.
Yasha,
Present, ma'am.
Shreyoshi,
Present, ma'am.
Chandri, Swapnil,
Present, ma'am.
Pratibhu,
Yes, ma'am.
Yes, ma'am.
Darpuk,
Yes, ma'am.
Yash,
Yes, ma'am.
Shomduti,
Present, ma'am.
Sambha,
Present, ma'am.
So I hope the variance calculation is clear to all of you. So in the next step, the similar kind of thing what we did in case of beta hat OLS that we have to do. So in the class of linear unbiased estimator, we have to check whether alpha hat OLS has the minimum variance or not. So that thing we have to do. Okay, so let's start with the value of alpha hat. And please consider all y as capital Y and all x as capital X. So alpha hat is equal to y bar minus beta hat x bar. Y bar you can write summation yi by n. And beta hat I'm replacing by summation wi yi. Already you did all these things. Beta hat is a linear in yi, so beta hat OLS is equal to summation wi yi. Okay. So it is summation wi yi into x bar. Remember, all the notations are capital. Okay, all the notations are capital. I'm changing the notation. For rest of the steps, please you do on your own. Okay. In the next step, I'm taking yi common. Okay. And writing the thing in this way. Summation 1 by n minus wi x bar into yi. Is it okay? Then I'm considering this summation, here I have summation 1 by n minus wi into x bar. Just I'll change wi by ci. Rest of the things are same. I'm changing wi by ci. Okay, and as I mentioned, all the notations are capital. So where ci is non-stochastic and ci can be presented as wi plus the difference between ci and wi. Instead of using the notation di, the difference between ci and wi, here I'm keeping the thing as ci minus wi. Okay, so I'm considering a factor a, which is summation 1 by n minus ci x bar into yi. Next step, I'm replacing y by the regression model alpha plus beta xi plus ui. The first component I'm keeping as it is. The second part I'm changing. I'm replacing yi. Then look at this step. Here you have alpha, and here there is the summation sign. So it is basically n alpha by alpha. Okay. Then
n alpha by alpha and n alpha by n.
N alpha by n, sorry. Yes, n alpha by n. N alpha by n. So the first term is alpha. The second term, beta, summation xi by n. So actually I'm using this 1 by n term first. I'll use this term later. So the first term is alpha, which is summation alpha, which is equal to n alpha by n alpha. Then beta, summation xi by n, so beta x bar. In the similar way, summation ui by n, which is u bar. So these are the first three terms while I am considering 1 by n and operating the sum. Next, alpha x bar into summation ci. Minus beta x bar summation ci xi. If you have any problem at any value, please let me know.
ম্যাম বলছি একবার আগের স্লাইডটা জানেন?
আগের স্লাইড?
হ্যাঁ ম্যাম, হ্যাঁ ম্যাম ঠিক আছে।
If anyone has any problem in the last three values, please let me know. Since x bar is a constant, always I kept x bar outside the range of sum. So the first term is summation Ci, the second term is summation Ci xi, the third term is summation Ci ui. Once you understand this step, in the next step, I am taking alpha common. So alpha is there in the first and the fourth term. So if I take alpha common, 1 minus x bar into summation Ci. Then I'm taking beta x bar common. Beta x bar is there in the second term and in the fifth term. Then u bar and the last term minus x bar summation Ci ui. Everybody understood up to this? If there is any query, any question, please ask me at this stage. Here, the alternative estimator is A. Okay, in the last case, we considered beta tilde. Here, A is the alternative estimator. A is an alternative to alpha hat ONS. Now, expectation of A is equal to alpha. That is, A is an unbiased estimator of alpha if, you know, summation Ci is equal to 0. If summation Ci is equal to 0, this part is equal to 0. So you will get alpha. And summation Ci xi is equal to 1. If summation Ci xi is equal to 1, you know, this part is 1 minus 1, 0. So this part will vanish. We will not bother about u bar and ui because when we will take expectation, whenever we will consider expectation of ui, the term will vanish. So when we will take expectation, these two terms will be not there as expectation of ui is equal to 0. So if I consider A to be an unbiased estimator of alpha, we need that summation Ci is equal to 0 and summation Ci xi is equal to 1. So these are the two constraints appearing from the precondition, that is A is an unbiased estimator of alpha. So from this precondition, we are generating these two constraints. Is it clear to everyone? Should I move to the next slide?
Yes, ma'am.
So under these conditions, I'm calculating the variance of the alternative estimator A. So variance of A is equal to expectation of A minus expectation of A whole square. Then A minus expectation of A, this part is simply this one, because summation Ci is equal to 0 makes it alpha, and the second term will be not there. So only the third and fourth term will be there. So we can safely write A minus expectation of A is equal to u bar minus x bar into summation Ci ui whole square. In the next step, I'm expanding the series u bar square plus x bar square summation Ci ui whole square minus 2ab. And then I'm operating expectation. Okay, so from the last part, you know, expectation of u bar square will be sigma u square by n. Then x bar square, actually here there are ui square terms and ui uj terms. So complete all these things in your home. there will be, this will be, you know, summation Ci square ui square plus double summation I running from 1 to n, j running from 1 to n, I not equal to j, Ci, Cj, ui, uj. So when you will operate expectation, from the first part you will get x bar square sigma u square, and from the second part you will get expectation of ui uj is equal to 0, so second part will be not there. Okay, so whenever there is a series, you have to expand this to understand how, using the homoscedasticity and non-autocorrelation assumptions, we are getting the actual values. Okay, and from this extension you will have summation Ci square. Now for the last term, when you will consider expectation of ui here, that will be equal to 0, and the entire term will be equal to 0 by that way. The entire term will be equal to 0 by that way. So we are getting variance of A is equal to sigma square by n plus x bar square sigma square into summation Ci square. Okay. Now for the OLS, this is the variance value. Okay. This is the variance value. Sigma square into 1 by n plus x bar square divided by summation xi minus x bar whole square. You know, so there is similarity in the values. I have to check what is happening for summation Ci square. So summation Ci square we are considering. Ci we defined as Wi plus Ci minus Wi. So summation Ci square is summation Wi square plus summation Ci minus Wi whole square plus 2ab. Summation Wi square already we calculated, 1 upon summation xi minus x bar whole square. Second term we are keeping as it is. Third term we are checking what will happen to this product. This product is summation Wi Ci minus summation Wi square. Then I am putting the value of Wi, which is xi minus x bar divided by summation xi minus x bar whole square. Already we proved summation Wi square is equal to 1 upon summation xi minus x bar whole square. Okay. Can we write the first term in this way? We have two constraints in our hand. Summation Ci is equal to 0 and summation Ci xi is equal to 1. So can we write the first term in this way? So can we write this? Basically it is summation Ci xi minus x bar summation Ci. X bar summation Ci is 0 and summation Ci xi is equal to 1. So that generates the first term to be equal to 1 by summation xi minus x bar whole square. So since both the terms are same, the value is equal to 0. So summation Ci square is equal to this one. So from 1 and 2, this is 1 and this is 2. We are getting variance of A is equal to sigma square by n was there, sigma square by n plus x bar square sigma u square summation ci square. We are getting this part. So we are using that concept, we are writing the thing. So it is sigma u square by n plus x bar square sigma u square. This summation wi square is 1 upon summation xi minus x bar whole square. That is the variance of alpha hat plus something. So look once again, this is x bar square, which is positive, sigma square positive, and it is summation ci minus wi whole square. So it is a positive number. The last term is a positive number. So variance of A is equal to variance of alpha hat plus a positive number. So variance of A is greater than variance of alpha hat, and thus alpha hat is the best linear unbiased estimator and satisfying the Gauss Markov theorem. So this is all about the properties of alpha hat. If anyone have any question for any part. The only thing you have to use the cap notation, otherwise the same thing. Any query?
Ma'am.
Yes.
Ma'am, could you go back to the last slide for a second?
Yeah. Do I need to write this state? Or I hope you are understanding this summation ci xi minus x bar summation ci is coming from this part, and using these two conditions I'm getting this to be equal to this. However, if anyone has any question. And should I move to the next one?
Ma'am, ek minute darabani.
Sure. Yes, because today I'll stop here. I'll not proceed further. This is the last thing. Actually, it is always better if we complete the properties of minimum variance properties of beta hat and alpha hat in a single day. Please let me know once you complete the thing.
Yes, ma'am.
Okay, so this completes the estimation part. Estimation of alpha hat and beta hat part. We need to discuss one more estimation that we will do in the next class. We have to find the acceptable estimator for sigma square, because under most of the circumstances, we will have no knowledge about sigma square. And if I have no knowledge about sigma square, actually I'll be not able to present variance of alpha hat, variance of beta hat, because all the variances of alpha hat and beta hat, these are based on sigma square. So we need to learn how to find out an unbiased estimator for sigma square. Because under most of the circumstances, instead of using variance of alpha hat, variance of beta hat, we have to use the estimated values of variance of alpha hat, variance of beta hat. In fact, you know, variance of alpha hat of this, variance of beta hat of this, estimated values. And for that thing, we need to learn how to calculate sigma square, or how to calculate the sample variance here, or what will be sample variance may not be the unbiased estimator. So actually we need to find out the unbiased estimator of sigma square. Any question, anything from this slide, or it's complete?
ওটাকে লিখেছেন ভেরিয়েন্স অফ আলফা হ্যাটের হ্যাট
Huh? I didn't get you.
ভেরিয়েন্স অফ আলফা হ্যাটের এস্টিমেটের হ্যাট পাশে যেটা লিখেছে
Next derivative.
আচ্ছা আচ্ছা
Then we
Ma'am.
will replace sigma u square by unbiased estimator. Naturally, that will be the estimated value of variance of alpha hat, estimated value of variance of beta hat. That I'll discuss next day, not today.
ম্যাম
Yes.
ম্যাম আগের স্লাইডটা একটু যাবেন?
This one?
হ্যাঁ ম্যাম, এক মিনিট।
This I'm closing the recording.